Article 4, Section 4 of our Constitution, of the U.S. Constitution, is the guarantee clause. And it says that the U.S. government guarantees a Republican form of government in each of the states of the Union. The Republican form of government is something that is subject to much interpretation. Some people say presently, gee, that means that we shouldn't have direct democracy, for example. Congress wisely hasn't touched that one. But it's largely a clause, Article 4, Section 4, that has fallen into disuse to address problems with the democratic process. Since the Reconstruction Amendments were added to our Constitution, we tend to hit up particularly the Equal Protection Clause to address issues with the democratic process. Such like stuff that Steve's working on now with the Voting Rights Act. But this clause in our Constitution was picked up and added to the constitutions of several other federal systems around the country, or around the world, including Argentina. And they have used this clause as justification for essentially setting aside the outcomes of democratic processes. So the federal government has the authority to intervene in provincial governments, set aside democratically elected state provincial legislatures, sometimes the whole judiciary, and put in place a federal manager. So the same words, the same text, plays out very differently from one context to another. Another example of rules behaving differently from place to place. On the plane ride over, I was, probably many of you saw this article in the Times, the Turkish Prime Minister, Erdogan? How do you pronounce this? Erdogan says, I've got an idea. How about make me president? Right? Now, the response in Turkey is that this is leading to authoritarianism, that he has ambitions to be an autocrat. In October, I gave a talk at Oxford, and on the plane ride over, read an article about Tony Blair having an idea that we ought to have in the EU a democratically elected president. And a similar idea, right, this kind of transition to, in the one case, a more lively presidential system, and the other one, introducing a presidential system, instead of being seen as Tony Blair's autocrat, it's like, this is just amusement. This is a guy who's out of a job, needs something to do, but it wasn't seen as a threat. So when we design rules or institutions, we have in mind a behavioral change that we think will result from that rule or that institution. And when it goes awry, when it doesn't work the way that we planned for it to work, often we blame, and if we run through the usual suspects as game various information issues, we blame culture. So here, one of my colleagues, Ron Engelhardt, has done his best to survey cultures around the world, right? He's gathered empirical evidence of the existence of distinct cultures by putting in place with a huge army of collaborators surveys where he asked people around a long battery of questions to gauge, which he then, through factor analysis, breaks down into two dimensions. To what extent is this a population that's focused on just getting by, survival, versus kind of moving up that Maslow's hierarchy to enlightenment, I suppose, right? And then on the other axis, to what extent, in terms of the way that they're structured, the organization of the government, is it traditionalistic, very hierarchical, or is it more secular, less presence of religion in the government, rational authority? Okay, and then we're able to discern clusters. Here's Northern Europe, North America. It looks like the U.S. from one battery to another made some progress on secular rational authority. But then we have Africa sitting a lot lower in this along these axes. So we can compare places like Sweden and Zimbabwe, and even though there's a heck of a lot of diversity within that population, we can talk about these cultures as being distinct. So when we talk about culture, how do we talk about it? Well, there are those who are out in the field and engaged in what here we call thick description, right? So we can identify cultures as being monogamous. Do they practice progenitor? Is there crop rotation? Is this the influence of the big man? There are those who, like Ron, takes from that, tries to take an aerial view and categorize and classify these cultures. Then there is this more game theoretical approach, where we classify cultures as behaviors such as, does this society tend to behave selfishly or cooperate? Do they punish in a game that we study? Is their typical offer in an ultimatum game something like $4.20? So what I'm going to do today is give you a background, think about the way that Scotty and I have been thinking about culture in games, which is along that last line of terms. Introduce this idea of the study of sequentially introduced institutions, which will help us understand this interaction between culture, behaviors, and institutional path dependence. I'll give you an example. Somewhere in the midst of this, I'm going to let Scott stand up and earn his plane ticket. And then we'll relate it back to some stuff that you might be familiar with, the Greif and Layton's work on endogenous institutional change. The essential idea that Scotty and I have been working on for like 10 years now is that people play multiple games simultaneously. So when we do our analysis of the way that people respond to a rule or a set of incentives, is that maybe what we're doing is partial equilibrium analysis if we're just looking at one independent game. And there may be an argument for thinking about these games existing in context, in a broader institutional context, and that therefore the way that an agent responds to one game is in some ways a function of the other games that agent is playing. Just pictorially, this is what I'm talking about. Here's an agent who has some interaction with, say, the law and government, her family and spouse, and environment and economy. And each one of these institutional environments probably has multiple institutions as well. So this larger project, we try to understand institutional performance as a product of culture, but also that culture is a product of the institutional environment. So how does that work? Well, in this multi-institutional setting, there is a behavioral response to one institution that at times can bleed over through what we call behavioral spillovers to affect the way that an agent responds to an entirely distinct set of rules. And so these two papers so far that we've published in this project, most recently an experimental study that came out in Games, where we found that there is significant spillover effects for certain categories of games. And so what we were able to do in that paper is talk not just about the existence of these behavioral spillovers, but make predictions about which games will spill over and affect which other games, and in what direction that spillover effect will take. That is, how will it shift behavior in that other game? So what we're going to do today is talk about sequentially introduced games. In that earlier work, it was a horizontal context, if you will, games introduced simultaneously. Now we're saying, is there such thing as institutional path dependence? That is, does the order that games are introduced affect the way that agents respond to those games? And if so, can we develop a theory that would help us predict when it might happen and when it won't happen, and what the outcome will be? we'll have these institutions arrive in sequence. Individuals will choose individuals' initial strategies. Sorry, this isn't stated. They'll choose an initial strategy that is, in the first game, that is payoff maximizing. But thereafter, some of the individuals will use heuristics, or they'll apply what they did in the first game to a subsequent game. And they'll learn equilibrium strategies. So we'll introduce these institutions from one epoch to another, but then within each epoch they're going to play the same set of games over and over again. So they'll have the opportunity to learn strategies within each epoch using best response dynamics. Okay, so here's what it looks like. These are games, not that we're studying in this paper, but these are ones that we used in those previous papers. So we looked at family of games that are all related to the prisoner's dilemma. So let's say in epoch 1 that we introduce subjects to a prisoner's dilemma. In this next epoch, and so they played that a lot until they arrived at some equilibrium behavior. Next epoch, they're still playing PD. Then we introduce a game that's closely related to the PD, but where the payoff maximizing behavior is actually on those diagonals, the off diagonals. So you win, then I win, you win, then I win. When we saw that in the lab, it was incredible to see people, sometimes they got to this, behaving in this alternating way. And if they get there, that maximizes their payoffs. It's still, they still have positive payoffs if they cooperate with one another, so they play all C. But if they manage to alternate it, they do better. And then another game, self-interest, where the dominant strategy is, well, we call it defect, but it's just to be consistent with the other games. But it's you don't need to worry about what the other player is doing at all. Okay. So these three games. Actually, what I'm showing you right now, we ran some experiments. We haven't published this yet, but this is the results of some experiments. So the first epoch, we set up in one treatment, players playing PD. Well, what you should notice first, by the time of the third epoch, they're all playing the same set of games. Okay. The difference is in what order were these games introduced. So in the first epoch, one group is playing PD, another group is playing that self-interest game. This is very easy to solve. This is a game where almost nobody screws up, right? Okay. PD, as we know, experimentally they don't get it the same way that we as game theorists get it. But they do quite well. Epoch 2, in the first path, PD, and then we introduce alt. Second path, self-interest, and then we introduce alt. So here the question is there a difference in the alt behavior? Right? And then by the third epoch, they're all playing the same games. But the question is there any variation within each game in the way they play? Okay, so what did we find? We found that they didn't all cooperate. So this little superscript here is indicating the behaviors. Okay, they didn't all cooperate in the prisoner's dilemma, but that is the plurality response. Self-interest, super easy game. We don't even need to talk about it. Was all D. In the second epoch, though, here, continuing to cooperate in the prisoner's dilemma, notice the difference in alternation. The A is an alternating behavior. Okay? C, cooperating. When alternation was paired with prisoner's dilemma, they cooperated. When it's paired with self-interest, actually a lot of them defected and just blew it. But they were more likely to alternate than they were in this treatment. So here we see what we call set dependence, okay? Where the way that you play in one game is a function of the other games in your set, the ensemble of games that you're playing. And moving on to the third epoch, by the time they're playing the full round, we see continuation of cooperation for alt and continuation of alternation for alt. But notice this completely wacky thing that they're doing in PD. They are alternating between the sucker's payoff and the, what do we call why am I blanking on that? Temptation, right, where you get away with exploiting the other person. We don't always see that in the lab in Prisoner's Dilemma. We would never expect that, and yet we see that here because of this path dependence, introducing the Prisoner's Dilemma after they've already played alternation. All right, so what we'll do today is simplify the class of games. And the results that we'll get out of this is that we're going to see that behavioral spillovers can produce suboptimal strategies, just like we were seeing with our experiments, right? We'll establish through a claim that path dependence will happen, is inevitable in the sequential introduction of games unless all of the institutions are insulated. And we'll define that later. Some of these games are more susceptible to path dependence and suboptimal play than others. So it isn't going to be the case that all games are affected, and we'll be able to describe which games will be affected and which won't. This is quite interesting. The most efficient paths of play, that is the payoff maximizing paths, tend to have very diverse early games. And we'll show you why that is the case. And then relating this back to the way that Greif and Leighton have been thinking about institutional change, if you have slow drift of an institution, and for those of you familiar with their paper, they have these quasi-parameters that are slowly changing the values of actions. Well, the consequence of this slow change is that shifting the play within an institution happens at the very last possible moment. And so that'll be inefficient. So in this model, we have, just like those 2x2 games I showed you earlier, just two actions, A or B. We have a set, or family of games, where theta determines the payoff structure of the game. So theta, I'll show you in a second, is something that we use as a key tool in relating the similarity of these games. And this theta exists on some interval. The payoffs to playing A, given theta, are decreasing in theta, and payoffs to playing B increase in theta. So what we can get there is this nice single crossing property that we are able to exploit, where on one side playing A is efficient, and then as theta grows, there's a threshold of efficiency, and then playing B becomes efficient. So that theta, I said, so what we need to, in this, we need a way of thinking of relating these games to one another. And so we do that through this theta. By having this theta, we're able to exploit this Euclidean distance between games, just based on shifting the value of theta. So then we can talk about one game as being closer or farther away from another game. And then we also introduce this gamma term, a spillover parameter. So we divide our population into two types of players. Those who are rational and just are able to see the full consequences and immediately adopt the payoff maximizing action. And those who, what we call heuristic learners. Those who grope around a little bit, and the way they grope is they start by playing the action that they played in the game that's most similar to this new one that they're playing. Okay. Now they still, in these series of rounds, can change their play, but this is where they start. Okay, so as I said in the initial game, all agents play the efficient strategy. In subsequent games, some play this efficient response and other payoff maximizing response, and others use this heuristic, and then they learn to play equilibrium using best response. And then the last definition, path dependence. a sequence of games produces path-dependent behavior if there's a permutation in the sequencing of games such that the play in at least one of those games would differ because of that sequence. So here's an example. So in this game, you can see how the payoffs, if they're coordinating their actions, A or B, is a function of theta. And then on the opposite, it is not a function of theta. Okay, so what you notice here is as theta increases, the value of playing A decreases, like I said before, and the value of playing B increases. So again, relating this, because we're really very much inspired by Graffy-Lincoln's paper, this is, you can think about this as being like their quasi-parameter, right? That can shift and change the value of the play. All right, so what we have here, given this, is this threshold of efficiency that I was describing before. So as theta grows, for half of that interval, playing A is payoff maximizing, and for the higher half of that interval, playing B is payoff maximizing. And another way that we can divide up this theta interval, and this is really the key point of our paper, is that given this gamma term, which is the proportion of our population who are these heuristic learners, we can use that to solve for these breakpoints, which define this interval into 3 sections. One section where the institution, here indexed by theta, is immune. That is, they will arrive at the payoff maximizing play, and an intermediate region where it's susceptible to the other games in context, and therefore the influence of these heuristic learners. So an example here. Let's start with game 1 where theta is 7. Now remember, our efficiency threshold is 8. So anything less than 8, the efficient play is A. Anything above 8, efficient play is B. So in game 1, theta will be 7, and the outcome is going to be everybody plays A. Game 2, theta is 15, so we're going to add an institution, this institution where theta is 15, and see an outcome of all B. Game 3, we're going to add theta of 9 and see what happens. Okay. So here we have theta at 7, and the play, the outcome of play is A, right? It's to the left side of the efficiency threshold. Then we add our second institution, theta at 15, and this is in that immune section, so it's not subject to the influence of what happened before, and the behavior, although the heuristic learners initially start by playing A, they conclude those rounds and in equilibrium finish by playing B. So the question is, once we introduce this theta, this game with a theta of 9, what the behavior is going to be. Now bear in mind, here's our efficiency threshold. So the efficient behavior would be B. So bear in mind that our heuristic learners are, so the rationals are going to play B here. But the heuristic learners are saying, gee, what game is most similar? So that, because that's their starting point. And so they start by saying, well, game with theta 7 is a lot closer than game with theta 15. So their rule is, I'm going to start by playing A. And then given best response dynamics, payoff structure, those rationals are going to coordinate their behavior with the heuristic learners in this realm. It wouldn't happen in the new realm. So this, I like this because this illustrates 2 points. First, that we're getting suboptimal play. Okay? And second, that the order of the introduction of these games matters. So we set up this claim. Any set of games with at least one susceptible game, one in that susceptible interval, and that interval is defined by a combination of the payoff structure and the gamma. Right? So with at least one susceptible game and 2 games that have different efficient outcomes can exhibit path dependence. And the proof of this is really easy, right? So if we have game A, a game where A is efficient, game B, a game where B is efficient, and game S, a susceptible game, right? If you have a combination first game A and then game S, that'll yield A and A. Okay. Game B, game S yields B, B. So increasing the spillover effect doesn't necessarily lead to more path dependence, but it will lead to more sensitivity to initial conditions. And let me show you. So for example, here we have the interval for that initial gamma that I set up, which really was 75%, of 6 to 10. But if I increase that gamma, that interval grows of the susceptible region. One other thing that we need to be thinking about here is a threshold, not the efficiency threshold, not those cut points, but the other, another one that these agents are using, these heuristic learners are using in order to decide what strategy to play, how to respond initially, right? Such that if, so we have this threshold, such that if beta is less than that threshold, they play A, and otherwise they play B. And this threshold is a function of the games that have been already played. But for that threshold, where does it end up after, I think this was 200 rounds of play, right? So that threshold, you notice here the susceptibility interval ranged from 0.2 to 0.8. And we see that about 25% of the time, I think it was, that cut point that agents are using ends up out on the extremes, right? And the other thing to notice is that it doesn't tend toward the efficiency point. So what this means is that most of the time, agents are not engaged in efficient play.
I'm here for tax reasons, because we both have to present we can't get our subsidy. So the quick thing here is when this is at 0.2 and 0.8, you see that there's just 200 runs. So basically half the time, as Jenna said, 25% or 25 times and 30 times, you get 0.8 and 0.2, and then you get stuff in the middle. When you push them out to 0.05 and 0.95, you get that over half the time you end up at the extremes. And the reason why is you've got a huge susceptible region, so whatever you get first, like if you get a B, that means the next time you almost certainly get something in the susceptible region, you end up getting all Bs. Okay? So how do you do this generally? So Jenna went through sort of a one-dimensional case. The paper's actually more general, so you can ask questions like, given a set of thetas, is there a sequencing that produces an efficient outcome? So one thing you could ask is, suppose you wanted efficient outcomes. So we're coming at this from a mechanism design standpoint. Like a mechanism design, the whole question is, how do you get efficient outcomes? But Jenna's initial point was that we often, what we're really doing is partial equilibrium analysis. We're only considering one institution. But what if you thought about there being multiple institutions and people's initial strategies being a function of what they played in the past? Now we assume case-based, but Bob, you could also assume maybe they're going to play what they played in the previous institution, right? That would be fine as well. It's a different assumption. But the point is that could you get a sequence? So what you can do is you can basically say, here's a set of games, and a path is going to be susceptible as if I play this thing up to this point, the outcome I get is not efficient. And basically what you need it to be the case is that if and only if like the lead-in, right, doesn't belong to the susceptible path. So how do you prove that in the context of a class of games?
Can you just go back to this?
Yeah. So basically what you're saying is that I can define a set of susceptible paths as the paths that would sort of mess me up, right? And you can only get efficiency if somehow the set of paths leading into this game don't mess me up, right? That's the result. Like, that's the sort of general abstract result. To prove that in the context of any set of games actually isn't that hard. So let's take a one-dimensional set of games, and let's let theta be the sufficiency threshold. So in Jenna's example, this is the 8. Okay? I can relabel the games as the ones that are less than the threshold and bigger than the threshold. And I label them sort of alpha 1, alpha 2, up to alpha m, and then beta 1, beta 2, beta 2. So the alphas are going up, the betas are going down, right? Now, what you can do is, given a set of games like this, okay, alpha 1, alpha 2, alpha m, beta k, beta 2, beta 1, any sequence of games where I take something from further out first leads to greater efficiency than if I take something closer in first. Does that make sense? So suppose I had a theta equals 15 and a theta equals 12. I'm better off doing the 15 before the 12, regardless of the rest of the sequence. Does that make sense? So, and then you can prove, I won't go through it because we're late on time, you can basically prove something called an index. So here's the idea. So I've got sort of alpha 1 equals 4, alpha 2 equals 7. So the first one's immune. The second one, I'd like to get an A outcome, but it's in the susceptible region. I've got this game, this beta game is 8.5, which is also in the susceptible region. The index for this game, too, says, how many of the B games can I introduce before I introduce this? And still get the efficient outcome? The answer is 0. I can't introduce any. And so basically the way the theorem works is you can basically look at sort of the index of each one of these games, right? And ask whether the index is large enough that I can keep pulling an A game, a B game, an A game, a B game from the extremes in order to get efficiency. So sort of as a benchmark, the way to think of this is I take the most extreme A game, then the most extreme B game, then the next most extreme A game, the next most extreme B game. However, I may want to violate that if it turns out I've got a bunch of really extreme B games. I might want to pull those in first. So it comes down basically to the distance of the games. Okay. One last thing on the this theta, as I mentioned, this is the quasi-parameter stuff from Greif and Layton. What's interesting here is that they talk about, you know, if you think of our framework, certain theta are going to be susceptible, some are going to be, and they think about, like, there's a theta that starts out at 5, then it moves to 7, then it moves to 9, and then it moves to 9.5, then it moves to 10, then it becomes B. So the interesting thing that they don't talk about, at least as far as I can tell in their papers, is that they talk about this being institutional change, but what they actually get, if you think of Marx standpoint, is when you get institutional change, it's sort of way beyond what it would be efficient to do so, right? It's at this point in our framework where the, you've gone with the immune region of the other game. Okay, so some quick takeovers. The larger behavioral spillover implies a larger susceptible region, right? Larger susceptible region implies more initial sensitivity, right? So in some sense, what games you played previously matter more, but a lot less path dependence. Right? So if there's a huge spillover, you sort of get on a train and you go to all B or I. Efficiency requires clear incentives early, right? So that's that theorem that, like, in order to get the good outcomes, you've got to start really with these extreme games. And then this other kind of, the outcomes are always at least as good with stronger incentives early, so you can't do worse. Okay, and then one last point, the, and I'll stop, is we're mostly through then, you can say, okay, we just did, Jenna showed this one example of one game, we've got the theorems for the one parameter games. If you take all 2x2 symmetric games, that's a 3-parameter family of games, and now you're just in a 3-dimensional space as opposed to a 1-dimensional space, and you can do the same thing. But instead of having a single index, you've sort of got there's only 3 possible games. You can play this corner, you can alternate, and you can basically sort of do the same thing, but you get the same result. You want to come in from the extremes. So the same sort of logic holds. If you want to get efficient behavior in the extremes, you've got to start with games that creates very, very clear incentives.
And I think that, I started this by showing how I care about constitutional design, and this, when we write these constitutions, what are we doing? Are we having an effect? But all of us care about social programs or have a sense of when things don't work out exactly as we plan. And an implication, I think, of what Scotty and I are onto here is, if you think about this, say that institutional drift, and we might think about, if we want to move a population in a certain direction, say introduce democracy, that we might want to design an institution that fits really well with their existing culture, that's an intuitive way to respond to that. But an implication of this that I really need to think through more is, no, you don't want to offer an institution that will just move them incrementally, because that can lead to this inefficient play. Instead, you might want to blow their doors off with something that's totally different and takes them out of their comfort zone and tries to generate a completely new behavior.